Greetings. Welcome to week 3 of operating systems. We've completed weeks 1 and 2. And so let's go ahead and do our dive into week 3. In week 2, we talked about processes. That was kind of our concentration. This week, we're going to concentrate on memory and memory management and kind of introduce that concept of virtual memory. Okay, so the main items that we're going to be talking about is the memory hierarchy, the memory allocation, how do we allocate memory, the concept of paging, where we're breaking memory up into pages. We'll get into a lot of detail on that. Segmentation, like talking about the logical address space and how we divide up memory depending on what function is being requested. Virtual memory, how we basically extend memory beyond the physical memory that we have. It becomes logical memory, and that's what we call virtual. Page replacement algorithms, how do we replace pages of memory in order to make processing more efficient? And then thrashing and performance, what are the causes, what are the effects? And so that's basically the items 2, 3, 4, 5, 6, 7, and 8 that we'll be talking about today. Again, concentrating on the memory side of the house. Okay, so the first thing we want to look at is the memory hierarchy. The memory hierarchy is organized such that it's there to balance speed, capacity, and cost. So if we looked at it, the first level of memory. So there's 1, 2, 3, 4, 5 levels of memory. The first is registers. Okay, registers is basically the closest item or closest memory space to a program. Okay, it basically keeps track of what program, what line is being executed, what PCP is there that needs to be looked at. The register is the fastest and the smallest piece of memory. It holds data for current instructions. What am I executing right now? Okay. The next level is cache. Okay. Cache stores recently used data and reduces access time to RAM. If I just had items, the theory here is that if I save data in cache, it's going to be reused again soon. Okay. And so if it's being reused again soon, then I don't have to go out into random access memory in order to get it because it's right here in cache. Okay. So depending on the size of your cache will either increase, okay, your processing or basically do nothing. Okay. Okay, so registers is the quickest, cache is the next, main memory, or RAM, or random access memory, is third. Okay, working memory for running programs and data. That's where your program resides. Secondary storage, okay, that is the third level memory. Non-volatile stores programs, files, SSD and HDD. I'm sure you're going to look that up. It's going to be on the quiz, okay? So go ahead and look it up now. Uh, uh, Tertiary backup storage, long-term storage, optical tape, tape, cloud, flash drive, okay, that sort of thing, or outside storage, okay, additional storage that you might add to your computer. So those are the 5 levels of memory: registers, cache, main memory, okay, and then secondary storage. Okay, memory allocation. Our operating system allocates memory processes using 3 approaches. One is contiguous allocation. Every process gets a single continuous block of memory. Okay, so just for explanation purposes, let's say we're talking about 1 meg. Okay, 1 meg of memory. And so contiguous memory says, I'm going to get process 1 meg of memory. I'm going to get process 2, 1 meg of memory. I'm going to get process 3, 1 meg of memory. Okay. Contiguous, each process gets a single continuous block of memory. Now, you notice it says contiguous, so it didn't say that I'm giving half the memory over here in the front part of the memory and the other half in the back part of the memory. This is contiguous. Okay, contiguous says they're contiguous from the beginning point to the end point. Okay, that's contiguous allocation. The next one is fixed partition allocation. Memory is divided into a fixed size partitions, okay, single, but can cause internal fragmentation. That's basically the situation where I said where part of your segment is in the front of memory, part of your segment is in the back of memory, part of your segment's in the middle of memory. Okay, so you're basically getting chunks of memory, okay, but it's in different places. It's not contiguous like we designated in contiguous allocation. So memory is divided into fixed size partitions, simple but can cause internal fragmentation. And then dynamic partition allocation. Here, partitions are created and demand vary in size, better use of memory, but can cause external fragmentation. That says that I'm not giving everybody a fixed amount. Program A might get 100K, program 2 might get a meg, program 3 might get 10K. So depending on the allocation, your dynamic partition allocation is not going to be consistent, with every process or every program that runs. Okay, so we have contiguous allocation, fixed partition allocation, and dynamic partition allocation. Key takeaway. Dynamic allocation provides flexibility, but requires good memory management to reduce fragmentation. Okay, fragmentation is the fact that I'm breaking memory up into pieces as far as the allocation, which obviously just means I have to go to different parts of memory in order to have my program execute. Okay, next is paging. Okay, paging eliminates external fragmentation by dividing memory into fixed size pages and frames. Okay, so out of that million bytes that I might get, I'm going to break that up into pages. Okay, so that's what we're explaining here. Paging eliminates external fragmentation by dividing memory into fixed size pages and frames. Okay, we have logical pages, okay, and physical memory frames. Okay, so here, my apologies. Sorry about that. My apologies. So here again, the logical pages that I'm basically building, okay, are basically dividing memory up into. I correspond that to a physical memory frame. Okay. So logical memory is divided into pages. Physical memory is divided into frames of one size. Any page can be placed in any frame. Okay, so it's not like there's a one-to-one correspondence between the page and the frame. Frame 1 might contain page 1 now. Frame 1 might contain page 100 later on. Okay, so there's not that direct connect, but it's basically saying that this logical page that I'm creating, I can put in one available frame that's physically in memory. Okay, so here we have a paging table. Okay, the paging table basically allocates and tells us where it's located physically. So in this case, I have page 0 is in frame 5. Okay, page 2 is in frame 9. So I keep track with the page table that tells me what physical location my logical page is. And so with that, I'm going to be swapping in and out of pages depending on what piece of data I need at a particular time in memory. Okay. So if I need logical page 3, then I will allocate it to a frame that's based on a physical piece of memory. Thereby, it's accessible by my program. Okay, segmentation. Segmentation divides a program into logical units or segments that reflect its structure. Okay. We can have code segments, we can have data segments, stack segments, heap segments. Okay, it's logical address space. Each segment, it has a base or starting address and a limit, the length of that particular segment. Logical address is less than the segment number and the offset. Not less than, but the logical address is the segment number and the offset into that segment. Okay. Segment table maps segments to physical memory. So I have a segment similar to what I did with the page, mapping it to physical frames. Same thing is here is happening. I'm taking a logical segment and I'm mapping it into a particular piece of memory that has a base location, okay, and an offset into that location. Still taking a logical piece of something and mapping it into a physical memory. So the key point, segmentation matches program structure and provides protection and sharing at a logical level. Key point on the page was pages removes external fragmentation and supports virtual memory through address translation. Again, translating a logical entity into a physical location. Both paging and segmentation are basically performing that type of function. So looking at virtual memory itself, virtual memory allows programs to use more memory than is physically available. You know, I have a 10 gig piece of memory. With virtual memory, I can say that I have a 300 meg of memory, where, 290 of that is virtual. Okay, so that's what's being explained here, that it uses disk space as an external physical memory. So I'm actually using what's on my disk drive as a address to where I can actually act like my program is accessing physical memory. Okay, so we got demand paging, pages loaded into RAM when needed. Okay. So what they're saying that I might have something that's out on disk. When I need that data, it's basically taken and brought into memory. Yeah, that's demand paging. Page fault is caused when a needed page is not in RAM. Okay, so I have a page fault. I'm looking for page 25. I look in memory and it's not there. That's a fault, which caused me to have to go out to RAM and find 25 and bring it into memory. Okay, swapping, entire process can be moved between RAM and disk. So I could take a process and save it, okay, into what we were calling virtual memory that's on the disk, okay. And then from there, that process is swapped in and swapped out, depending on when it needs to execute. So the key point, virtual memory provides the illusion, and that's what it is, an illusion of a large private memory. Each process while using the disk as backup. The disk is taking and making that physical memory virtually larger than it really is. Page replacement algorithms. Okay, when the RAM is full, the operating system chooses a page to replace, make room for a new page. It could be FIFO, first in, first out. The first page that came in is the first page that's going to go out. The least recently used. If the least recently used page means that nobody's accessed it in a while, so I'm going to take that page and I'm going to swap it out to bring in my new data. Or optimal. Yeah. Optimal replaces the page that will not be used for the longest time in the future. Yeah. I'm not going to need this, even though it may be recent, I'm not going to need that page anytime soon. So that's optimal. It says I'm going to take that page, swap it out, and then swap in the page that I need information on. Okay, goals, page replacement. The goals are minimize page faults, maximize throughput, and balance the CPU. Key point, good page replacement algorithms reduce page faults and improve overall system performance. Okay. We have this concept of thrashing that can occur. Thrashing occurs when the program or when the system spends more time swapping pages than executing processes. So if I'm spinning here, I'm swapping a logical page out to disk and going to disk and bringing back another page. And I'm just constantly doing that, back and forth, back and forth. Okay. I could be spending more time in the back and forth than the actual execution of the program that's using the pages. Okay. So that's thrashing. And that's what we have here. Cases of thrashing, too many processes competing for limited frames. Okay. So there's a lot of swapping. So you have 10 programs that are swapping in and out. Okay, that can cause thrashing. High page fault rate. A lot of pages aren't in memory for the ones I need. Insufficient physical memory. It may be the point that I'm thrashing because I just physically don't have enough physical memory, even though I have a virtual memory to go along with it. Okay, so effects of thrashing, very low CPU utilization, okay, high risk activity, poor system throughput. It is bad when we start thrashing pages. Prevention strategies, working set model, keep pages each process is actively using. Okay, that's the working set. Page fault, maintain page fault rate within range. Okay, so when I get out of that range, I basically stop that process from executing until later on. Allocate more frames when the page faults increase. Key point here: thrashing severely degrades performance. That's the key thing. Programs, one of the things say, why is this program running so long? This program is running so long because I'm doing a lot of thrashing. I'm getting a lot of page faults, and that page fault is causing me to go out to the disk and do some thrashing. So I'm thrashing back and forth, which is taking time for me to actually running my program. One of the reasons we could have that why things might take a little longer than we anticipate. Okay, so that's it for week 3. Review this, be ready for the little quiz I'll have for you on Tuesday. And if any questions, let me know. So let's continue on. See you on Tuesday on week 3. Have a good one. Bye.